In this video, we're going to be looking at question 23 of the Unit 2 sample paper for IAS Chemistry from Edexcel. Now, this question is an unusual question in terms of what you've done previously compared to Unit 1, because this is a section all on its own, and it is called the Synoptic question. And what it means is it's one singular question that covers a range of different topics or a range of different subtopics. So the entire question will revolve around iodine and chlorine, just asking different parts. Now, what you have to be aware of for these types of questions is you could be asked anything from Unit 1 or Unit 2. The bulk will be Unit 2, but they might pull in a little bit of Unit 1, particularly calculations or bonding and these sorts of questions. So just be aware that you are expected to have remembered and learned from Unit 1. You can't just sit the exam and then forget it. Everything in chemistry builds on these. So for this question, we have got iodine monochloride, which is ICl. We are told that it is a covalent compound that is produced by the reaction of iodine with chlorine. It is a dark brown liquid at room temperature, and the equipment here, our U-tube, can be used to pass the chlorine over the solid iodine to produce the iodine monochloride. And you notice here that they say chlorine gas as well. When the excess chlorine is passed through the U-tube, it reacts and we can get iodine trichloride in an equilibrium reaction. So this part here will come into play more as we go through the question. So part A, very simple, 2 marks. Write a chemical equation for the reaction of iodine with chlorine to produce the iodine monochloride. So we've got our ICl being produced from the I2 and the Cl2. Nice and easy, but don't be caught out by the state symbols. There was a reason that I underlined each of these. The iodine monochloride is a liquid, the iodine is a solid, the chlorine is a gas. So you must make sure to put these state symbols in. So you've got iodine, which is diatomic, as a solid, plus chlorine, which is of course also diatomic, giving you a gas. And we are going to make ICl as a liquid. And for any chemical equation, you're always expected to balance. So we just put a 2 in front of the ICl. You'll get 1 mark for getting the correct species and the balancing, and 1 mark for your state symbols. Part B is talking about the permanent dipole that we have in iodine monochloride, and we want to complete the table using the electronegativity data from the data book and then show the dipole on the diagram. This should be one of the easiest questions in the entire paper, because to fill in the electronegativities, you simply go to the data book and you look them up. So we have got chlorine, which is 3, and iodine, which is 2.5. And all we have to do is put those numbers into our table. So there's 3 for the chlorine and 2.5 for the iodine. We must also put the dipole, so please remember that the more electronegative element is going to take the electrons closer towards it, meaning it becomes slightly negative. So in this case, our delta negative is our chlorine, and our delta positive is our iodine. For part 3, the iodine monochloride reacts with propene to form 2 isomeric products. This is an addition reaction that is similar to the reaction of propene with the hydrogen halides. Now, this is a very common technique in the synoptic questions, where they give you a question that is very similar to something that you have done in class, but you have to apply what you have learned to an unfamiliar situation. You have never done the addition of iodine monochloride being added onto an alkene, but you have done the hydrogen halides, and it works in very much the same way. So a lot of this section is application of what you have learned in the content. That's what makes it different from section B, which is more recall and regurgitating. Section C is a lot more application. So we have to think about what is actually happening here. So the best thing to do is draw out. We know that we have got propene. So what will that look like? Well, we have a CH3, a CH, a double bond, and a CH2. It does say that we need the skeletal formula of both isomers, so we also need to draw out what it looks like when it is in skeletal form. And we are going to be adding the ICl. That means that we would have one adding here and one adding there. And the fact that these are isomers means that we can have either iodine on carbon number 2 and chlorine on carbon number 1, or vice versa. So again, we have to think about what happens where we're going to draw the propane, because we have that sort of base as the propane, and then we're going to add on the iodine and the chlorine. So the iodine could go in the center, like that, or it could bond for the chlorine on carbon number 1. So remember that you do need to have that extra sort of leg coming off of the propene, or the propane backbone, and that tells you that you have 3 carbons connected to the chlorine. And then you do the same thing, but this time you swap the iodine and the chlorine, and those are your 2 skeletal isomers. We now have to explain which of these isomers is the major product. So what we have to think about again is this is very similar to when you have electrophilic addition of a hydrogen halide. If we have a sort of analogous here, we've got the hydrogen is basically the same as the iodine, because both of these would be our delta positives, and our delta negatives, the halogen, would be the same as the chlorine. And this all comes down to the carbocation. So we have got which of these 2 products is going to be the major based on the carbocation that is being formed. So we need to think, where do we want the positive charge to be? And we actually want the positive charge to be on carbon number 2, because that gives you the secondary carbocation, which means your more positive iodine is going to have to add on to carbon number 1, meaning this is going to be your major product. So firstly, you have to identify it by naming it. So that substance is 2-chloro, 1-iodo-propane. Remember, your 2 chains should always come alphabetically. It doesn't matter that the iodine is on carbon number 1, the I comes after C in the alphabet, so the chloro comes first. And we need to then explain why. So we have our delta positive iodine is being attracted to the double bond. That's our area of high electron density. And it is then attacked by the pi electrons. So the electrons that are in the pi bond, that's where the curly arrow would be. And that is very similar to if it was a delta positive hydrogen. That means the iodine joins to carbon number 1. And when it does that, it forms the secondary carbocation. And because the secondary carbocation is more stable than the primary, it forms the major product. And the major product, therefore, is when the chlorine adds to carbon number 2. So we are explaining what is happening here. We have the delta positive iodine being attracted into the double bond and getting that curly arrow coming out from the double bond onto the iodine, allowing that to then join and bond in with carbon number 1, leaving your delta your positive charge and the carbocation in the centre, giving you the secondary carbocation, meaning it is more stable and then allows the chlorine to join. Moving on to part D, we are now looking at the actual equation between the iodine monochloride and the iodine trichloride. So this is where we get the excess and form this equilibrium. And we are told that we've got a brown liquid and we have a yellow solid. So that's going to be important when we're talking about our equilibrium. So first of all, we want to state and justify one precaution that must be taken when preparing the iodine trichloride. And the most important thing is this here. The fact that you have got chlorine gas, you are going to have to use a fume cupboard. So your precaution is the fume cupboard, and the justification is because chlorine gas is toxic. So it's not something that we want to be breathing in. You don't want to even do this in a well-ventilated laboratory. You always want to do this in a fume cupboard. For part 2, we are now looking at oxidation numbers. So we want to give the oxidation number of the iodine in both of the compounds. Iodine is one of those substances that can change its oxidation number. So we have to think about what is happening here. So if I have the ICl, well, chlorine, the more electronegative, is always the negative. So that's going to be -1, meaning that must be +1. Therefore, our first answer is +1. When it is ICl3, we've got the -1, but we have 3 of them, meaning that gives me that overall charge of -3. To balance that out, my iodine must be +3. So my second answer, +3. 1 mark for getting both of those correct. For part 3, the iodine trichloride can also be made by reacting potassium chlorate 5 with iodine and hydrochloric acid, and they give us the reaction. By considering the oxidation numbers for the chlorine, explain whether or not this reaction is a disproportionation. So we're going to have to work out the oxidation number of the chlorine in each of its compounds. So let's take them one at a time. We have KClO3. So the potassium is always +1 because it's in group 1. The oxygen is always -2 because it's not in a peroxide, but I have 3 of them, so that gives me -6, meaning my chlorine is +5. So in my KClO3, I have a +5. For my HCl, very simply, the hydrogen is +1, the chlorine is -1. Then I go over to my products. I've got KCl, so the K again, +1, and my chlorine is -1. And then for my ICl3, well, we already answered that the iodine is going to be the +3 and the chlorine is -1. So we have to look at what has actually happened here. Well, we have got a reduction happening from the +5 to the 1-, but we don't have oxidation. The chlorine is not changing its oxidation number to show an oxidation reaction. Therefore, this is not a disproportionation, as the chlorine is not oxidized and reduced. Remember, for disproportionation, the same species has to undergo oxidation and reduction. Moving on to part E, now we are looking at some calculations, so bringing back in some content from Unit 1. We are told that chlorine has a molar volume of 24,000 centimetres cubed per mole, and the conditions used in this reaction. We want to show that the density of the chlorine gas is approximately 3 grams per decimetre cubed. So what we have to do is think about, well, how do we calculate density? And density is the mass divided by the volume, making sure that your mass is in grams and your volume is in decimeters cubed. So let's first of all work out the MR of the chlorine. That's going to be 2 times the 35.5. And of course, you can look that up in your data book or on the periodic table if you can't remember. So that is 71 grams. And our molar volume is going to be, grams per mole. Our molar volume is 24,000 centimeters cubed per mole, which when we put into decimeters is 24 decimeters cubed per mole. So now all we have to do is substitute those numbers in, which is 71 over 24, giving you an answer of 2.96 grams per decimeters cubed, which is approximately 3. So this is a nice way to check if you have got the correct answer, just by making sure that you have matching answers to the value that they give you in the question. For part 2, it tells us that air has a density of 1.25 grams per decimeter cubed, and if the U-tube used in part D, so the previous question, or the previous part of the question, is inverted as shown in the diagram, the solid yellow iodine trichloride produced turns into a brown liquid. And we have to say what is happening here. So just as a reminder, our equation was the ICl as the liquid plus the chlorine as a gas, which is going to give you the ICl3 as a solid. So we need to be able to explain why we are making this brown liquid. And hopefully you can see it's going to be linked into equilibrium. We are clearly moving the position of equilibrium to make more of the iodine monochloride. And we have to figure out why this is the case. So we've just worked out that the density of chlorine is approximately 3 grams per decimeter cubed. That was done for a reason. You weren't just asked that randomly. If you then compare that to the density of air, we can see that chlorine is more dense. So we know that chlorine is more dense than air. So when we invert this U-tube, it is going to leave the U-tube because it is going to fall below the air and then fall out the bottom of the U-tube down at the bottom here. So when that is the case and we have got less chlorine and the chlorine gas is leaving, it causes the concentration of the Cl2 to decrease. If we decrease the concentration of the Cl2, this shifts the position of equilibrium in this reversible reaction over towards the reactants. So it shifts to the reactants, which is the left-hand side, forming more iodine monochloride, which is a brown liquid. So by having this inverted U-tube, we have the chlorine leaving the U-tube at the bottom, causing our position of equilibrium to shift to the left to help replace the chlorine and put it back into equilibrium, which then moves the solid iodine trichloride into the liquid iodine monochloride. And the last question here is an empirical formula. So this is definitely a callback to Unit 1, where we have got the mass of 0.64 grams of iodine reacting with the fluorine to form 1.31 grams of a fluoride of iodine. And we want to calculate the empirical formula. So the best way to do an empirical formula is to draw a table. So you're going to have I and F as your elements. You're going to have your masses, which we can take from the question. So we know the iodine is 0.64 grams, and the fluorine is going to be the 1.31 minus the 0.64, because conservation of mass tells us that our mass of our reactants must equal the mass of the products, which gives you a mass of 0.67. Our relative atomic masses of iodine and fluorine can be taken from your data book or from the periodic table, which is 126.9 and 19. We then calculate the number of moles, which is simply the 0.64 over 126.9, which gives you 5.04 times 10 to the minus 3, and then the 0.67 over 19, which is 0.034, and then to get our whole number ratio, we divide both of these by the smallest number. So we're going to divide both of them by 5.04 times 10 to the minus 3, which of course is going to give me 1 for the iodine, and for the fluorine, it is going to give me a value of 7, or 6.99, but we round it up to 7. Therefore, our empirical formula is IF7. That is the 20-mark Section C Synoptic question for the Unit 2 sample paper. As you can see, it is all about iodine, but it calls back to different parts of the course. So we touched on some redox, some equilibrium, and then some calculations as well from Unit 1. So please make sure that you do practice these types of questions, and you do make sure that you remember what you did learn in Unit 1, because any type of question could come up. If you've got any questions on this, please feel free to leave a comment below and check out the other past paper walkthroughs on this channel.